So this is part 4 of numerical methods for partial differential equations practice final exam, starting with number 11. Consider use of t equals k use of xx on the interval from 0 is less than x is less than 1 with Newman boundary condition use of x of 0 comma t equals 0 and Dirichlet boundary condition u of 1 comma t equals 0. Part A, construct the second order finite difference approximation for the Neumann boundary condition. Part B, explain how ghost points may be used. Part C, derive the modified matrix system for backward Euler. Part D, discuss whether symmetry is preserved. And Part E, explain how boundary discretization can reduce global accuracy. Okay, so this is a boundary conditions and accuracy problem. So at x equals 0, u sub x of 0 comma t equals 0. Second order one-sided approximation is -3 u sub 0 plus 4 u sub 1 minus u sub 2 over 2h equals 0. So u sub 0 equals 4 u sub 1 minus u sub 2 over 3. Alternatively, using a ghost point, u sub 1 minus u sub -1 over 2h equals 0, and this implies u sub -1 equals u sub 1. Then from here, u sub xx, 0 comma t, that's approximately u sub 1 minus 2 u naught plus u sub -1 over h squared equals 2 u sub 1 minus 2 u naught over h squared. And for backward Euler, u sub j to n plus 1 minus u sub j to n over delta t, that equals kappa times the quantity u sub j minus u sub j plus 1 to n plus 1 minus 2 u sub j n plus 1 plus u sub j minus 1 superscript n plus 1. So our interior rows remain tridiagonal. The first row is modified by the Neumann condition. The last boundary satisfies this u sub n superscript n plus 1 equals 0. Depending on the ghost point treatment, symmetry may or may not be preserved. A carefully constructed finite volume style discretization often preserves symmetry if the boundary approximation is the only first order accurate. The global solution accuracy can drop from second order to first order. Okay, so that's number 11. Moving along to number 12. Let a finite difference method for a linear initial boundary value problem be written abstractly as u to the n plus 1 equals b sub delta t, comma sub there delta x, u to the n plus delta t f to the n. Assume the exact solution restricted to the grid satisfies u to the n plus 1 equals b sub delta t, comma sub delta x, u to the n plus delta t, f to the n plus delta t, tau to the n. Okay. Sorry. Talking so fast. Probably shouldn't, but letter A, define the error e to the n equals u to the n minus capital U to the n minus lowercase u to the n. Part B, derive the error recursion. Part C, state a stability estimate sufficient for convergence. Part D, prove a convergence bound in terms of truncation error. Part E, explain the relationship between consistency, stability, and convergence. So an overview of this convergence proof framework. And this is just an overview. The numerical method is u to the n plus 1 equals b sub delta t, comma delta x, u to the n plus delta t, f to the n. The exact grid solution satisfies u to the n plus 1 equals b sub delta t, comma delta x, u to the n plus delta t, f to the n plus delta t, tau to the n. If we define e to the n equals capital U to the n minus lowercase u to the n, and then here e to the n plus 1 equals, we subtract here, we subtract, and then e to the n plus 1 equals b sub delta t, comma delta x, e to the n minus delta t, tau to the n. And from there, iterating gives us e to the n equals b to the n e naught, e to the 0 minus delta t. And the sum from m equals 0 to n minus 1 b to the n minus 1 minus m tau to the m. If the initial data are exact, then e to the 0 equals 0. And if we assume stability here, we have the norm b to the k is less than or equal to c. And for 0 is less than or equal to k delta t less than or equal to t. Then from here, the norm of e to the n less than or equal to delta t, that's sum m equals 0 to n minus 1 c of norm t to the m. Sorry, I wrote this kind of fast. My apologies if I mispronounced anything or the lettering is a little nebulous or whatnot. My apologies. So therefore here, norm e to the n less than or equal to c t max m norm t m. And if that tau t, that's just a tau, I'm sorry, tau to the m. And if tau to the m approaches 0 as delta t, delta x approaches 0, then e to the n approaches 0. So consistency plus stability implies convergence. My apologies if I mispronounced anything there. Went through it rather quickly. And last one, number 13. So for the explicit heat equation scheme here, this is what we're given. U sub j n plus 1 equals r u sub j minus 1 n plus quantity 1 minus 2r u sub j n plus r u sub j plus 1 to the n. Part A, B, C, D, respectively. Part A, show that if 0 is less than or equal to r is less than or equal to 1/2, the method satisfies a discrete maximum principle. Okay, and for part B here, explain why this implies L infinity stability. Part C, explain why r is greater than 1/2 can lead to oscillations. And part D, compare this maximum principle argument with von Neumann stability. So this is maximum principle and monotonicity. Okay, sorry about the misspelling there. Part A, the explicit heat scheme is use of monotonicity. I'm sorry. Did I say monotonicity? So here, the explicit heat scheme is u sub j to the n plus 1 equals r u sub n, r u sub j minus 1 to the n plus quantity 1 minus 2r u sub j to the n plus r u sub j plus 1 to the n. And if 0 is less than or equal to r is less than or equal to 1/2, then all coefficients are non-negative and sum to 1. R plus quantity 1 minus 2r plus r equals 1. Thus, u sub j to the n plus 1 is a convex combination of neighboring values. And therefore, this min j u sub j n is less than or equal to u sub j n plus 1, less than or equal to max j u sub j n. And this is a discrete maximum principle. And for part B here, it implies norm here. The infinity norm here, u to the n plus 1 is less than or equal to the infinity norm of u to the n. So the scheme L infinity is stable. Part C, if r is greater than 1/2, then the coefficient 1 minus 2r becomes negative. The update is no longer a convex combination, so spurious oscillations can appear. And for part D, von Neumann stability examines Fourier modes. The maximum principle gives a stronger monotonicity based argument in physical space. Okay, so that's all for part 4, and thank you very much and have a great day.